So, welcome to Chicago. One of the few companies over here is local over here, and so for the last 2 days we talked. We heard a lot about what's the new regulations and what are the new technologies that can be applied and how do we go to the next level of emissions. But one thing we have learned, and I'm going to try to talk more and as we go through, is in the end it always boils down to what does our customer wants. In the end, if they are happy, we are happy. And who we are, basically Progress Rail. It's a rail division of Caterpillar. It's a formation of two companies, Electromotive Diesel, which has been for almost last 75 years. It was previously by GM, and then later sold to a private equity and later bought by Caterpillar, and Progress Rail Services, which was bought by Caterpillar in 2006. So together we have the entire portfolio of rail servicing and OEM and servicing. Primary business segments is locomotive, both transit and freight cars. We actually have just entered the transit market after a long pause, and I'm going to talk a little bit about that. And obviously, anywhere where they need engine from 3,000 to 6,000 horsepower, we do sell that mainly in the marine, the stationary mobile power unit. If you guys are first time visiting in Chicago, one of the tourist attraction is the Willis Tower. And if for any chance there is a power failure, that whole building is powered by one of our engines. So we are headquartered in Albertville, Alabama, and our local office is there or the engineering headquarters is in LaGrange, which is exactly 15 miles west of where we are. We have a global presence, pretty much. So there's and I think I'm going to talk a little bit on the next few slides. There are 65 or 66,000 locomotives which have been sold by EMD, and 30,000 of that are still active. So with that, it makes us one of the largest locomotive manufacturers in the world. We sell in every countries. Actually, there you go. In almost 75 countries for the line haul, and we actually just entered the transit business, the passenger car. This is in collaboration with our colleagues in Caterpillar with the C175 engine. It's a high-speed engine, and it's a high-speed locomotive. So you can see aerodynamics is one of the key players there. This is actually one of the first Tier 4 locomotives in the transit applications. I'm going to go a little bit more in details, and it was basically a joint venture with Progress Rail and Vossloh, which is now Stadler. The locomotives we make are sold in different countries, and this is kind of a quick overview. And every country has their own requirements. Every country have their own regulations. Every country, the railroads are either managed by the government or it's a private entity. So one of the things when we were called Electromotive Diesel or EMD, we used to also call us every model different, because every locomotive we make has something unique to it. So these are some of our standard locomotives which have been sold throughout the globe. Moving into the power products business, that's again a big portion of our portfolio, and for the last 2 years I've been very active in the power product market. Together, EMD and Caterpillar, we have a big market share in the inland river boat application, which is one of these boats. The interesting thing about the inland river boats is if they are going south in the Mississippi or up, they're going to go pretty much full throttle and stay there for 10 to 14 days. They're going to dock, have a crew change, and then go back in full load. that's basically you have a lot of mileage or the megawatt per hour. They accumulate a lot of those. The other ones are the tugboats. These are used mainly when you have to push or steer big ships. They do not require a lot of power all the time, but when they do, they want the maximum torque they can because they are pretty much steering the entire ship. OSVs, that's a very interesting. That's one of challenging. So for the oil rigs, these OSVs will start in the morning, go full load to the oil rigs, and idle the whole day, and work with whatever the things they need, and then again go back to full load, come back to the shore. Ferries, obviously, you have a more of a passenger type where you kind of go from a no load to some 50% load, stay there, and then pretty much go in the transit. We also sell our engines into the large cruise ships or the bunkers, but our engines are used mainly as an auxiliary power, and that's a quite different market. Those are pretty much standby engines. They are at a fixed RPM, and depending on how much of auxiliary power is needed, it goes up and down. So with a big diverse market, a wide range of requirements, when we were entering the tier 4, we were faced with the question that is there any one solution that fits all, or do we have to tailor different solutions for every different market segments we are targeting. Just to give a quick kind of a tier 4 for the locomotive, there was no tier 4 interim. For the locomotive or the rail application, it went from tier 3 to the tier 4. And the tier 4 was 0.13 NOx in grams per horsepower hour and 0.03 PM in grams per horsepower hour. Marine had a tier 4 interim with the provision that if you can stay in a tier 3 couple of years longer and directly go into tier 4 final, and both were pretty much implemented in 2015. Again, just to give you an example, the IMO 3, which the marine, we have a lot of those. The NOx target is very similar. They don't have a PM, but again, the weightage is pretty similar. On the right, we have the chart. It's basically you have a RPM versus power, and the size of this bubbles dictates what's the weightage for each one of these load conditions in your FTP duty cycle. You can see there's a the red ones are the marine. There's a quite heavy weightage in the higher load points. Rail, it's kind of a different scenario. You have a very big weightage on idle, dynamic brake, and the lower notches. What's not shown here is if you go to a switcher cycle, these bubbles for the rail application on the higher loads starts to shrink, and the ones on the notch 1, 2 are basically kind of 30% load conditions start to grow there. There's a lot of weightage on the part load condition, so it's quite a challenge at that point. So with that, now again I said our tier 4 started in 2015. Most of the heavy duty applications were ready with the tier 4A in 2007. So we had a bunch of engineers in the room and said, okay, let's see what they have done, and it should be easy. It shouldn't be that challenging. So we approached a lot of component manufacturers, especially on the after treatment side, and we asked them, okay, what have you got? Let's start from there and see if we can use any of the after treatment system. So they came back with a catalyst kind of this big. And for the given flow, what we have in the large engine, you actually need a lot of those. So this is again, we did a work with with Union Pacific, and this report is there in the California ARB website. So the exhaust comes and gets distributed into four, I don't know if you can see in the back, four plenums like these, and each one gets divided into 3 of those. So in other words, there were 36 of those sub-catalysts which were the flow was distributed into. It looked pretty cool. We used to call it the Millennium Falcon from the Star Wars because it looks like a starship. When we used DOC and passive DPF, it worked good. The flow, we all know DOC is a porous block. It's kind of a self-balancing act. So if you have more flow going in the other, the resistance goes up. So we were good with that. But the challenge came when we were using any form of an active region, or if we started to use any of urea injection. If you start adding injectors over there and start injecting, your flow will never be uniformly distributed. It's very difficult to measure transient distribution of flow at all these individual legs. So you're over-injecting ammonia or DEF on one of the legs versus the other. You started seeing a lot of slip. Very similar example on the active region too. So that's when one of our starting challenges was packaging. Now you have 36 to 40 of these small bricks which you are trying to put together. How do you put it together, and how do you even support this entire structure? On the locomotive. There was one other work we did with UP under the same funding. We were looking into adding an EGR loop on the EGR, basically a cooled EGR concept. And what I have over here, that's our EGR module. If you take EGR coolers, those which were available back in 2008 timeframe, most of the EGR cooler on the heavy duty, if you look in the tube and shell, the coolant goes through the exhaust goes through the tube, and the coolant goes through the shell. It's kind of a different nowadays for the larger engine. You basically have the flow going through the shell and the coolant going through the tubes now. So you have a different fouling effect. But at that point, you had to use a lot of the smaller EGR coolers in parallel, which was taking a lot of real estate. And if you think a locomotive being a big engine and there's no space constraint, it's quite a challenge. So we are having issues with the EGR cooler, or how to size it properly. Do we just keep on lengthening the length? We had some issues with the blower. Now, this is something quite different from a 4-stroke, because our primary engine is a 2-stroke engine, and it always needs a positive pressure delta. So you need some form of a positive displacement device to take the exhaust energy and push it back. We were getting, and that's quite uncommon in the industry. So we're not able to get the right size blower which kind of operates through the entire spectrum. So with all these, in our very early stages, we were struggling, or we were trying to make an understanding what would be the optimal solution. So at that point, we went back to our customers and understand what does our customer actually wants. You can meet the same emissions using either an after treatment solution or an in-cylinder solution. And again, as I talked about the various applications we serve, our rail customers, and again, the big customer is the regulatory bodies. We need to meet their requirements the first. The railroad, safety is the primary component. Safety, reliability, they want their locomotive when they need it to be functional. And one thing which they really wanted is a urea-free solution. And main reason is most of the railroads have their own network of fueling, and adding another fluid to it is going to add a lot of cost. Marine, on the other side, is a completely different scenario. Obviously, we have the regulatory requirements. If you look in a marine application, we are the engine OEM. We do not make the entire ship. In the shipbuilding process, you have the naval architects who design the ship. For them, it's a matter of which one fits in their engine room, which one doesn't make their engine room too cluttered, which does not make their engine. So when we are talking to a lot of naval architects, one of the things they specifically mentioned is it's much easier in a boat to lengthen it than increase the height, because that changes your stability. If you're adding after treatment system, try to keep in the same plane as the engine, so that you're not changing the location of the center of gravity. These things makes a lot of difference from an engine OEM and how the naval architects are going to decide which engine they will be using. The shipyards, they want to minimize the construction cost. They don't want the engine goes in once and then have another setup where the after treatment is mounted. They just want a drop-in concept, which is one of the main primary concerns. But the most important is the people who are going to use the boat. They obviously want to spend the least amount of money on fuel. They want some thermal efficiency back from the engine with the lowest DEF consumption, and keep it as simple as, they don't want that transition that you are now adding 10 different knobs, but the operator shouldn't see 10 different knobs at the same time. You need to add the simplicity into it so that you're not scaring the customer. And one big thing is minimize the risk of regulatory violation. If there is anything, if for some reason the urea doser or the pump fails, the engine should be smart enough to record that information so that they can take that information and submit it to the regulatory bodies that we had this failure from this time to this time, and it should be a simple process as a USB plug-in and download the information. And this is again required by the regulatory bodies also. So with that, just to give few of the solutions for the locomotive application, it's a SD70 ACE, which is our Tier 4 locomotive, and it's a 4-stroke engine with a cooled EGR solution. You can see in a couple of slides back, I showed you how the EGR cooler space was. Now, I don't know if okay. This is our entire EGR cooler. So we are able to package it down and able to minimize the risk of EGR fouling. We have a common rail system with a double wall, and again, safety is the primary concern. We need to make sure that there's no, with the high pressure, there's no fuel leakage, or if they happen, it's well contained. So we have a double walled fuel injection system, 2-stage turbocharging system. The powertrain is completely isolated, so that if you, from the higher peak cylinder pressure, you might have a higher vibration levels. So it's completely isolated so that the cab operators does not get that impact. And again, a lot of things which locomotive customer wants. So once again, in a quick nutshell, the fuel efficiency, it's actually one of the best in the industry. Reliability is something which we need to continuously improve. We have entered Tier 4, and as we go into the next regulatory limits, one thing we have to keep on going is the reliability. As I keep on mentioning, there are more locomotives in the field before I was born. So in the locomotives we are selling right now are still going to be operating the day I retire, and I'm relatively young. So that's where the life expectancy is expectation from the customer. So if we are doing something today, how do we accommodate the next generation of regulations, and how do we meet those? Those are things which we have to think about from now onwards. The F125 locomotive, this is a collaboration we did with our joint it shouldn't be a collaboration. It's basically just calling our colleagues in Caterpillar. It's a C175 with a urea system. It's a very, I would say, one of the smartest after treatment system I've seen. It uses a Z flow concept, and it works very good. It's a high-speed engine, so it's and it's mainly on the passenger locomotive side. We have it's coming in the market for the Metrolink application in California, so you should see some coming soon. The marine solution. The marine is kind of very interesting. I kind of talked about a lot of the requirements, but one of the big requirement is for the locomotive, and especially you saw the 2 slides back, the after treatment system, the serviceability. That's one of the key issues with it. If you look at how a locomotive is serviced, it goes into a shed, the hood comes out, and they can take the entire after treatment system out and do the servicing or take another module and drop it in. Marine, it's completely different. You are tucked in an engine room way below, and if you need to take anything out or the engine out, it's close to $10 to $12 million investment, because you have to cut anything up there, which is as expensive as a new boat. So the concern was, I need to service the after treatment system if I need to in the engine room. So what we started looking into is, what are the other components, other areas we can combine it with. We had this accessory rack in the back, where a lot of the things which were not part of the engine mounted were mounted over there. We started optimizing those. We went from a single lube oil with a paper filter to a high pressure oil filtration system, saving some space so that we can accommodate the after treatment system. Each boat is built completely differently, so they don't know at this point where the outlet for the after treatment system will be. So we have multiple outlet flexibility, and the one of the unique thing on this one is it's a simple plug and play. This whole thing comes and it gets dropped into the engine. So the regulation perspective, the shipyard's responsibility reduces significantly. Again, heat rejection is one of the areas we have worked very closely. But again, we don't want to reinvent the wheel every time. Caterpillar have the air-assisted urea injection system, which they have perfected for the C175 and on many other engines. We use those, what they have already worked on. A lot of things, closed crankcase ventilation was implemented because we didn't want the challenge with the face plugging. We had a very adaptive calibration method. I talked about the OSVs, where you go into in the morning, the operator goes to a full load, goes into the oil rig, sits there idling for 8 hours. You are depositing hydrocarbon in your catalyst. Now when you come back, you go to full load. If you start injecting urea right away, you just deposit the urea on the top of the hydrocarbon, your catalyst performance goes down. We have done these idle tests in the test cell, and we have found a way where you can actually let the catalyst burn off the hydrocarbons and then start injecting the urea. So there's a time delay in there which meets the which doesn't deteriorate the quality of the catalyst. Fuel efficiency, that's the big thing. We want to make sure we preserve the fuel efficiency and increase the thermal efficiency of the engine. Marine engines are big into transient response. We go from this can be one of the Tesla ads to, we go from no load or idle to full load in 13 seconds. Actually, in the past, our valor test for the marine application was 11 seconds. And we need to preserve those. So there's a lot of energy coming towards the after treatment system, making sure the after treatment system can handle that. Vibration, we need to make sure it can support the 3G of vibration, which the after treatment system might be seeing on a locomotive. Actually, it's slightly higher, and for the marine, it's around 2G, where it kind of hits the on the other side. So with that, I would leave few minutes for some questions, but just a quick, I wanted to give you a quick flavor of what are the different solutions. One thing which is any solution we already have or will come in future, it's always driven by our customer. What do they need? And it's a long process. It's gonna take a few more years because this is just a starting point. It's gonna continuously get tweaked or improved, and then we'll come to there'll be always a better solution tomorrow. So if anyone has any questions, well.